podcast. This is Mr. White.
And Mr. Johnson.
And today we're going to visit the ideas of work and energy.
Wow, wait a second. Work?
Work. Physics work, not
Actually doing the work.
not doing your classwork, but actually physics work.
I was going to say, these podcasts are supposed to be short. You can spend the whole day on talking to them not doing the work.
Yeah. So let's concentrate on a few things. First of all, good news for them, there's only one kind of work.
That is good news.
Good news. But there are lots of kinds of energy.
Yeah, energy is a big thing.
Big topic. Shows up in all of your science classes. So help me out, Mr. Johnson. What kind of energy is there?
Well, we talked about it today before the investigate. There was potential energy.
Okay.
There's kinetic energy, which
Okay.
kind of go hand in hand.
They can, yeah.
Well, I mean, I know not for this class, but there's chemical energy.
Mm-hmm. We're going to talk about a second kind of potential energy. So there is gravitational potential energy,
Okay.
which is due to an object's height
That makes sense with gravity, yeah.
with gravity, yeah. There is elastic potential energy, which has to do with bendy stuff,
Maybe like a pole vault?
like a pole vault, kind of like the investigation.
Okay.
And then kinetic energy, of course, is due to an object's motion, which is a revisit to chemistry, the kinetic molecular theory of gases, of course, which they all remember.
I'm sure they do.
I'm sure they do. So these are the three types of energy we focused on in the investigation. And then there's work. And I like to give two different definitions of work. I like to think of work as force acting over a distance. That's a good definition.
It's the one I remember.
And work is the ability to add energy.
Interesting.
To add, how about, or take energy from a system.
And they should know what systems are, since we talked about it in chemistry as well.
Right. So we can, in chemistry you guys talked about heat transfer.
Right.
And
Exothermic, endothermic.
adding energy to the system, or the system releasing energy. Well, that's that add-take. This is the newer thing, though, force acting at a distance. So if you push on an object and it moves, you're doing work on the object. And now that it's moving, you have given the object kinetic energy.
So is that why they have that saying, like if you're pushing on something and nothing's happening, you're just twiddling your thumbs?
Yeah, you're not working. You're not doing any physics work, at least. If you were to do work and pick an object up over your head, what kind of energy have you given it?
Gravitational.
Gravitational potential energy. And when you take that rubber band you find on the floor and you do work to stretch it out and point it at the kid across the classroom, what kind of energy have you given the rubber band?
Well, it's elastic, definitely, because it's rubber.
Elastic potential energy, right?
Now, what do you do when you let go of it?
So when you let go of the rubber band, it's above the ground, so it does have some gravitational.
Right.
You release it, so now it's moving, and that elastic has now become entirely kinetic.
So you've transferred energy.
You have transferred energy.
Nice.
Work and energy are transferred. That's a really important idea.
So you didn't create it, you just transferred
Yeah,
it.
not created, not destroyed,
That sounds like a law.
not lost. And so what is that? That is the law of conservation of energy. I like the mathematical versions. The change in the energy is equal to zero of
Meaning?
any system, or the initial energy is equal to the final energy, and you could say that the change in energy is equal to the work done on an object. So there's a lot of ways to talk about that. Regardless, we are still accounting for all of the energy in the beginning and all of the energy in the end, and all of the stuff we do in between.
Okay.
Okay? So let's go back to our concepts of work, kinetic energy, gravitational potential, and elastic potential energy. They all have equations.
Oh, that's what the equal signs are for.
Oh, yeah. And so kinetic, we said motion, okay? And from chemistry, it was half the mass times the speed squared, okay? This is going to be a familiar term, mass. And V, of course, is speed. Gravitational potential energy, we said, is a result of the object's height.
Right.
But M is also important, mass, times our acceleration due to gravity, times the height. Very important as well.
It's all familiar terms.
Right. So G is acceleration due to gravity.
Now, not to get off topic, but there are certain units for this too, correct? Because I know in chemistry and mass we use grams, centigrams, kilograms. Is there a preferred one in physics?
There is a preferred one in physics. And the best part is all four of these topics, why we're talking about them all at the same time, all measured in joules. Joules, joules. Named after a British physicist, James Prescott Joule. He did some of the first heat work, thermodynamics. Didn't really care about kinetic and gravitational energies. He cared about heat transfer. But the unit is named after him. We defined work as force over a distance. So that's all it is. Force times the distance. Done.
Isn't work sometimes called a Newton meter?
Yeah, it could be a Newton meter. So a joule, okay, it can be a Newton meter because it's a force times a distance measurement. That works as well. Not to be confused with the Newton-Meton, which is a made-up term that I had a student use once on a test.
You stumped me. I thought it was something that we're not using.
The Newton-Meton. Yeah. And then the hardest one is elastic potential energy, just because it's new. Half times, that's a cursive K, times a distance squared.
Some of them don't know what a cursive K is.
That's a cursive K. And this refers to the spring constant. And it refers to the springiness, not sure how you spell that, the springiness of a substance.
Okay.
So, like your car's shock, or, your car's shock has a high spring constant, because it's going to take a lot of force to move that thing around. That's exactly what you want. A rubber band has a very low spring constant. A bungee cord, if you were to bungee jump, has some value somewhere in between. Okay? It references how hard you have to pull or push to stretch or compress that object.
Okay.
Okay. And then x is the distance of stretching or compressing.
So stretching or compressing. Now, if we were to apply this to the pole vault example, would X maybe be how much the pole vault bends?
Yeah.
Is that another way to think of it?
When you go back to your investigation, okay, so here's your ruler. Of course, you're pushing down on the ruler here, so it can't go anywhere. All right. And then you've got your washer up here. You applied a force down, and so this distance X, that's how much you stretched it. This is also the distance you applied the force over. So you did F over D, and you stretched this in spite of the K value. So you gave it elastic potential energy by doing work on it. And then when you let it go, it flies up and is now in motion. So now it has kinetic energy, and at the top of its path it quits moving, but it's in the air really high, so it has...
So by quit moving, that means it changes to potential, and since it's in the air, gravity always has it.
Right.
Okay.
So if I redraw that so it's a little cleaner, and we can see the whole event. Okay? We do work on it down to give it elastic potential. The washer leaves the ruler and has a lot of kinetic and a low amount of GPE. At some point, it's going to have equal amounts of the two. At the top, it's going to have just gravitational potential. On the way back down, at the same point, it's going to have equal amounts again. Okay? And what we start to notice is then the GPE gets lower and lower while the KE gets higher and higher. Now then when it hits the ground eventually, it stops because there's a force applied over it over a very tiny distance. Mm-hmm. So the ground must be doing work. You put work in, the ground does the same amount of work on the way back.
So it's like one big cycle.
Yeah, it's the conservation of energy, where the beginning and the end have to be the same.
So then everything you did starting with the work is what you're going to have at the end. So all of this added all together, initial and final, is going to be equal to the work.
Whatever work I put into it here is the same amount of work the ground has to do here. Whatever work I put into it here is the gravitational potential energy it has here.
So when the students were complaining on how hard it was to get well, we used pennies in my class.
Okay.
How hard it was to get the penny in the air, they shouldn't be complaining because the ground's doing the same amount of work and it's just sitting there.
Right. And then it's really important, the gravitational plus the kinetic at any one of these spots is equal to the amount of work we did. So it doesn't matter what point we pick, energy is the same all the time.
It's pretty cool.
The last thing I want to talk about briefly is a guy named Richard Feynman. So when I was a kid, my favorite basketball player was Michael Jordan for a lot of reasons. He was good, for example.
Good?
Yeah, the best. He was the best.
I think the best is
He
good.
was the best.
Better than Kobe for all you out there.
Better than LeBron.
Yeah, better than LeBron.
Better
definitely.
than LeBron. They might disagree with that.
Well, whatever.
Okay.
6 championships.
But I have a favorite physicist. And this guy right here, Richard Feynman, is my favorite physicist. He won a Nobel Prize. Probably should have won 2. He did everything from help invent the atomic bomb. When I was a kid and the Challenger space shuttle exploded, he was the guy that came on TV and explained what had happened and why it all went wrong. And he valued his ability to teach physics to college students. And he has this great explanation about energy. He compares it to blocks. So let's say my son wakes up and he has 9 Lego blocks. And he plays with those Lego blocks all day. And at the end of the day, we always make him clean up. And we can only find 8 of the blocks. Mm-hmm. Well, we look around, and sure enough, what do we find? We find the 9th block. So the amount of blocks he has at the beginning of the day is the same as the amount of blocks he has at the end of the day. He gets the blocks out tomorrow. He plays with them. He loses not 1, not 2, but 3 blocks. And we can only find 6. And we search, and we search, and we may have to look hard. We may have to dig and dig. But sure enough, the 7th and the 8th, and eventually the 9th block appears. So he described energy as a block idea. If you start the day with 9 blocks, there are still 9 blocks at the end of the day. You may have lost it, you may not be able to find it, but eventually that block will turn up. He describes energy in exactly the same way. The toy just doesn't disappear. The energy just doesn't disappear. You just have to look hard enough and you will find it.
And as a side note, those blocks get disappeared, and it is sometimes impossible to find them.
Those little Lego blocks. You step on them in the middle of the night, usually.
Or you think they have legs and they walk away.
Yeah, you didn't know that.
Wow.
So I believe that covers energy and energy conservation. Signing off, this is Mr. White.
And Mr. Johnson.